NASA just pulled off something that's never been done before. For 40 days straight, one of their newest spacecraft stared at a comet, not once a day, not once an hour, every 4 minutes, for nearly 6 weeks. And in that footage, they captured something extraordinary. Not just the comet they were tracking, but a brief glimpse of something else, something that shouldn't even be there. An interstellar invader, 3I Atlas, the ancient visitor from another star system, photobombing NASA's comet surveillance, zipping left to right beneath the main target like a cosmic interloper. This is the story of two comets, one discovered by an amateur astronomer scanning old satellite images, one from beyond our solar system. Both captured in the same footage by a spacecraft that's rewriting the rules of how we study these cosmic wanderers. From August 25th to October 2nd, 2025, NASA's Punch mission tracked Comet SWAN with unprecedented frequency. And in doing so, they caught something no one expected. I'm going to break down exactly what NASA captured, why this 40-day surveillance is such a breakthrough, and what that brief glimpse of 3I Atlas reveals about the invisible forces shaping our solar system. Let's start with the spacecraft that made this possible, because Punch is one of NASA's newest missions, and most people have never heard of it. Punch stands for Polarimeter to unify the corona and heliosphere. It's designed to do something revolutionary, create a complete 3D map of how the sun's outer atmosphere, the corona, connects to the solar wind that fills our entire solar system. The corona is the sun's outer atmosphere. It's incredibly hot, millions of degrees, and it extends millions of kilometers into space. But we can't see it most of the time because the sun's bright surface overwhelms it. The only time we can see the corona from Earth is during a total solar eclipse, when the moon blocks the sun's disk. For a few precious minutes, the corona becomes visible as a ghostly halo around the darkened sun. But Punch doesn't need an eclipse. It uses instruments called coronagraphs, artificial eclipse makers that block the bright disk of the sun so the faint corona can be observed continuously. The heliosphere is the bubble of space dominated by the sun's influence. It extends far beyond the planets, all the way to where the solar wind meets interstellar space. Punch is mapping how energy and matter flow through this vast region. The mission is led by Dr. Craig DeForest, the principal investigator from the Southwest Research Institute in Colorado, and his team just achieved something that may be unprecedented in comet observation. They tracked Comet C 2025 R2 SWAN every 4 minutes for nearly 40 days, from August 25th to October 2nd, 2025. According to NASA, this may be the longest any comet has been tracked with such a high frequency. DeForest explained, "Other comets have been tracked at once-per-day cadence for years. What's new here is the few-minute cadence of observation." Think about that difference, once per day versus every 4 minutes. That's 360 observations per day instead of one. That's 14,400 images over 40 days instead of 40. Why does this matter? Because comets are dynamic. They brighten and dim. They develop jets. They fragment. They interact with the solar wind in complex, rapidly changing ways. And to understand these processes, you need continuous observation. You need to see every change as it happens, not just daily snapshots. That's exactly what Punch delivered. A near-continuous movie of a comet as it drifted through the inner solar system, and the results are absolutely stunning. Now let's talk about the comet itself, Comet C 2025 R2, SWAN. Because this object has a remarkable discovery story that shows how modern astronomy really works. Comet SWAN was first spotted in September 2025 by Vladimir Bezugli, a Ukrainian amateur astronomer. But he didn't discover it by pointing a telescope at the sky. He discovered it by doing something much more clever. Bezugli was scanning publicly available images from SOHO, the Solar and Heliospheric Observatory. This is a spacecraft that's been watching the Sun continuously since 1995, operated jointly by NASA and the European Space Agency. SOHO has coronagraphs that block the Sun's bright disk, allowing it to see the faint corona and any objects passing near the Sun. And because all of SOHO's images are made publicly available online in near real time, anyone can access them. Bazugli was systematically going through these images, looking for anything unusual, and in September 2025, he noticed a bright blob close to the Sun that hadn't been there before. That bright blob was a comet, a new comet, one that had never been catalogued before. The comet was designated C2025 R2 SWAN. The C means it's a comet. The 2025 R2 indicates it was the second comet discovered in the second half of September 2025, and SWAN refers to the SOHO wide-angle and narrowband coronagraph, the instrument that captured the images Bazugli was analyzing. Here's what's remarkable. Just one day after Bazugli's discovery, the comet reached perihelion, its closest point to the Sun. It passed at a distance of 46.74 million miles, or 75.20 million kilometers. To put that in perspective, that's about half the distance from Earth to the Sun. It's closer than Mercury's orbit, close enough for intense solar heating. The timing of the discovery was crucial. If Bazugli had been a few days later, the comet might have already passed perihelion and started fading before anyone noticed it. But because he caught it just in time, astronomers around the world were able to mobilize their telescopes and track it through its most active phase. This is a perfect example of how amateur astronomers contribute to professional science. Bazugli doesn't work for NASA or ESA. He's not affiliated with a university. He's just someone with the knowledge, dedication, and sharp eyes to spot something new in publicly available data, and he's not alone. Amateur astronomers discover dozens of comets every year by scanning SOHO images. It's become a global citizen science project, with people from all over the world contributing to our understanding of the solar system. Now let's look at what Punch actually captured during those 40 days. Because this time lapse is unlike anything we've seen before, this is the complete sequence. Hundreds of images stitched together, showing Comet SWAN gliding through space over nearly 6 weeks. At the top of the frame, you can see Mars. That bright object that stays relatively stationary is the red planet. At the bottom, you can see Spica, the brightest star in the constellation Virgo. It's actually a binary star system about 250 light-years away. And between these two landmarks, Comet SWAN drifts from right to left, its tail streaming behind it. You'll notice thin black seams running through the image. These are boundaries between individual snapshots. NASA released this time-lapse before the images were fully processed, so these seams remain visible, but they don't detract from the science. They actually help us see how the sequence was assembled. In the early images from late August, you can see Comet SWAN has a bluish-green coma, that glowing cloud of gas and dust surrounding the nucleus. That color comes from diatomic carbon, C2 molecules, and cyanogen gas. When these molecules are hit by ultraviolet light from the sun, they fluoresce, emitting that characteristic greenish glow. But watch what happens by mid-September. The coma starts to change shape. It develops an unusual triangular form that astronomers call a hammerhead shape. This distortion is often linked to a fragmenting nucleus. When a comet's core starts to break apart, outgassing from multiple pieces can stretch a normally round coma into a lopsided triangular form. What's happening is that the comet isn't one solid chunk anymore. It's breaking into pieces, and each piece is releasing its own jets of gas and dust. The combined effect creates this weird, asymmetric shape. Now watch the tail. As Comet SWAN moves leftward in the images, its tail is pushed in the same direction by the solar wind. The solar wind is a constant stream of charged particles flowing outward from the sun at about 400 kilometers per second, nearly 1 million miles per hour. When this wind hits the gas and dust in a comet's tail, it pushes it away from the sun. But here's what's interesting. Because the tail is being pushed leftward, the same direction the comet is moving, it makes the comet appear to drift backward, like it's being blown along by the wind rather than flying through space under its own momentum. Of course, that's just an illusion. The comet is moving in its orbit around the Sun, following the laws of gravity. But the tail's behavior creates this visual effect that makes it look like the comet is surfing on the solar wind. Now, here's where this story takes an unexpected turn. Because Punch wasn't just tracking Comet SWAN, it accidentally captured something else. Near the end of the sequence, in late September or early October, watch the lower portion of the frame carefully. There. Did you see it? A faint object zipping left to right beneath Comet SWAN. That's 3I Atlas, the interstellar comet from another star system, the third confirmed interstellar visitor in human history, photobombing NASA's comet surveillance. At that time, late September 2025, 3I Atlas was passing through the inner solar system on its hyperbolic trajectory. It had already passed perihelion on October 29th. Wait, that can't be right. Actually, let me correct that. If Punch captured 3I Atlas in late September or early October, and 3I Atlas reached perihelion on October 29th, then Punch caught it just before or right around its closest approach to the Sun. The fact that both comets appeared in the same field of view is pure coincidence. They're not physically close to each other. They're millions of kilometers apart. But from Punch's perspective, they happen to be in the same direction at the same time. And you can see the difference in their motion. Comet SWAN drifts slowly across the frame over 40 days, but 3I Atlas zips through in just a few frames. That's because it's moving much faster, about 58 kilometers per second, or 130,000 miles per hour. That extreme speed is what confirms 3I Atlas is interstellar. It's moving faster than the Sun's escape velocity at that distance. It's not gravitationally bound to our solar system. It came from interstellar space, and it's going right back out there. So in this one time lapse, we're seeing two completely different types of objects. Comet SWAN is a native of our solar system, probably from the Oort cloud, that vast sphere of icy bodies surrounding the Sun at the edge of its gravitational influence. But 3I Atlas is from somewhere else entirely. It formed around a different star in a different planetary system, possibly 7 to 10 billion years ago. It's been wandering through interstellar space for millions of years, and we just happened to catch it passing through. This might be the first time two comets, one local, one interstellar, have been captured in the same continuous observation sequence. It's a cosmic coincidence that gives us a unique opportunity to compare them side by side. Now let's talk about what this 40-day observation actually teaches us. Because this isn't just about pretty pictures. This is about understanding the invisible forces that shape our solar system. The solar wind is not uniform. It's not a steady breeze. It's turbulent, with fast streams and slow streams, dense regions and sparse regions, magnetic structures and shock waves. Comets act as natural tracers of the solar wind. Their tails show us where the wind is blowing, how fast it's moving, and how its structure changes over time. In the Punch time lapse, you can see Comet SWAN's tail isn't constant. It brightens and dims. It wiggles and waves. These variations are caused by changes in the solar wind. When a fast stream of solar wind hits the comet, the tail gets pushed harder and stretches out longer. When a slow stream passes by, the tail relaxes and becomes shorter. The solar wind also carries the Sun's magnetic field with it. When this magnetic field interacts with the ionized gas in a comet's tail, it can create beautiful structures, kinks, disconnection events, and plasma tail separations. Gina DiBraccio, a heliophysicist and acting director of NASA's Solar System Exploration Division at Goddard Space Flight Center, explained the importance of this work. Watching the Sun's effects from multiple vantage points and with different types of instruments is what gives us a complete picture of the space environment. We use these same tools to track and analyze how space weather impacts our astronauts, our spacecraft, and our technology here on Earth. Space weather isn't just an academic curiosity, it has real-world consequences. Solar storms can damage satellites, disrupt GPS signals, interfere with radio communications, and even knock out power grids on Earth. For astronauts in space, whether on the International Space Station or future missions to the Moon and Mars, space weather is a serious radiation hazard. A major solar storm could deliver a dangerous dose of radiation. By continuously monitoring the solar wind and how it interacts with objects like comets, Punch is helping scientists improve space weather forecasting. The better we understand these processes, the better we can predict when dangerous conditions are coming and take protective measures. Comet SWAN, tracked for 40 days with unprecedented frequency, is a perfect test case. Scientists can analyze how its tail responds to every change in the solar wind, building detailed models of these interactions. Now let's talk about what happened after the Punch observation period ended, because Comet SWAN's journey didn't stop on October 2nd. In late October 2025, Comet SWAN made its closest approach to Earth. The distance was 25.10 million miles, or 40.38 million kilometers. That's about 105 times the distance to the Moon. So it wasn't a particularly close approach by comet standards, but it was close enough to be visible through binoculars and small telescopes. At that distance, Comet SWAN was on the cusp of naked-eye visibility. Under dark skies, away from city lights, someone with excellent vision might have been able to see it as a faint fuzzy patch. Amateur astronomers around the world captured beautiful images of Comet SWAN during this period. Backyard telescopes revealed the comet's greenish coma, its developing tail, and the ongoing changes in its structure. And those observations confirmed what the Punch images suggested. Comet SWAN was fragmenting. Multiple pieces were visible in high-resolution images, each with its own small coma. Comets fragment for several reasons. Thermal stress from solar heating can crack the nucleus, rapid rotation can tear it apart, outgassing can create internal pressure that blows chunks off the surface, and sometimes comets are just loosely bound rubble piles that fall apart under their own weight. For Comet SWAN, the combination of close solar heating at perihelion and the stresses of outgassing were too much. The nucleus broke into pieces, and those pieces are now slowly drifting apart as they continue their orbit around the Sun. Over the coming months and years, astronomers will continue to track these fragments. They'll watch how they evolve, how they fade, and whether any of them survive or completely disintegrate. Now let's do something interesting. Let's compare the two comets that appeared in Punch's footage, because the differences between them tell us a lot about the diversity of objects in our galaxy. On the left, Comet SWAN. On the right, 3I Atlas. Comet SWAN is from our solar system. It probably spent billions of years in the Oort cloud, that vast spherical shell of icy bodies surrounding the Sun at distances up to 100,000 astronomical units. Something, maybe a passing star, maybe a gravitational perturbation, nudged it inward, sending it on a journey toward the Sun. 3I Atlas is from another star system entirely. It formed around a different sun, in a different planetary system, possibly 7 to 10 billion years ago. It's been wandering through interstellar space for millions of years, encountering 93 different stars over the past 10 million years alone. Comet SWAN has a typical composition for solar system comets. It's dominated by water ice, with smaller amounts of carbon dioxide, carbon monoxide, and various organic compounds. That's why it has that greenish coma. The color comes from carbon-based molecules. 3I Atlas has a completely different composition. It's dominated by carbon dioxide, about 8 times more CO2 than water. That's the reverse of normal comets. This unusual chemistry tells us that planetary systems around other stars can be very different from ours. Comet SWAN behaved like a typical comet. It brightened as it approached the Sun. It developed a coma and tail. It fragmented under thermal stress. All of this is normal, expected behavior. 3I Atlas has been doing things that shouldn't be possible. It's losing more mass than it weighs. It has a 16-hour heartbeat, a periodic brightness variation that's too precise to be natural. It has multiple jets that pulse in synchronization, and it has a tail pointing toward the Sun, not away from it. The comparison tells us that while comets share some basic characteristics, they're icy bodies that outgas when heated, the details can vary enormously depending on where and when they formed. Our galaxy is 13 billion years old. It contains hundreds of billions of stars, and around many of those stars, planetary systems have formed, evolved, and sometimes been destroyed. Each system has its own unique chemistry, its own history, its own quirks. When an interstellar visitor like 3I Atlas passes through our solar system, it's like receiving a sample from another world, a message in a bottle from a distant shore. And by studying it, we learn about the diversity of planetary systems across the galaxy. Let's take a moment to appreciate the technical achievement that Punch represents. Because tracking a comet every 4 minutes for 40 days is not easy. First, the spacecraft has to maintain precise pointing. It can't drift, it can't wobble. It has to keep the comet in its field of view continuously, even as both the spacecraft and the comet are moving through space. Second, it has to transmit all that data back to Earth, hundreds of high-resolution images. That's a lot of data, and it has to be sent across millions of kilometers of space using radio waves. Third, all those images have to be processed, calibrated, aligned, stitched together into a coherent sequence. This requires sophisticated software and powerful computers. Previous comet observation campaigns have been impressive. The Rosetta mission orbited Comet 67P for 2 years, providing unprecedented close-up views. The Deep Impact mission actually crashed a probe into a comet to study its interior. But Punch is doing something different. It's providing continuous high-cadence observations from a distance. It's showing us how comets interact with their environment in real time. It's capturing the big picture, the comet, the solar wind, the heliosphere, all in one frame. And this is just the beginning. Punch will continue operating for years, observing more comets, more solar storms, more interactions between the sun and the space around it. The techniques developed for Punch will inform future missions. Maybe we'll have spacecraft that can track multiple comets simultaneously. Maybe we'll have constellations of satellites providing 360-degree coverage of the inner solar system. ESA's Comet Interceptor mission, scheduled to launch in the late 2020s, will take this even further. It will wait in space until a pristine comet from the Oort cloud or an interstellar visitor is detected, then fly out to intercept it and study it up close. Let's zoom out and look at the bigger picture, because this story is about more than just 2 comets. It's about how we study the solar system in the 21st century. Modern space science is increasingly collaborative. Punch observes from space. Ground-based telescopes observe from Earth. Amateur astronomers contribute discoveries and observations. All of this data is shared, analyzed, and synthesized. Comet SWAN is a perfect example. Discovered by an amateur astronomer scanning SOHO images, tracked by Punch for 40 days, observed by professional and amateur telescopes during its close approach to Earth. Each contributor added a piece to the puzzle. 3I Atlas has been even more collaborative. Hubble observed it. JWST observed it, Mars orbiters observed it, ground-based observatories around the world observed it, and Punch caught it in passing. This coordinated campaign has given us an unprecedented view of an interstellar visitor, and all of this data is being shared openly. NASA makes its images and data publicly available. So do ESA and other space agencies. This open science approach accelerates discovery and allows anyone, professional or amateur, to contribute. Citizen science projects like the SOHO Comet Hunters have discovered thousands of comets. Projects like Galaxy Zoo have classified millions of galaxies. Projects like Planet Hunters have discovered exoplanets. Astronomy is being democratized. You don't need a PhD or access to a major observatory to make meaningful contributions. You need curiosity, dedication, and the willingness to learn. Vladimir Bezugli, the Ukrainian amateur who discovered Comet SWAN, is proof of this. He's not a professional astronomer, but he made a discovery that led to a major NASA observation campaign. This is the future of astronomy: collaborative, open, accessible, with professionals and amateurs working together to explore the universe. So what happens next? Where do we go from here? Punch will continue its mission, observing the sun, the solar wind, and any comets that happen to pass through its field of view. Over the coming years, it will build up a comprehensive data set of how the heliosphere behaves. Comet SWAN's fragments will continue their orbit around the sun. Astronomers will track them, watching how they evolve and fade. Some fragments might survive for years. Others might disintegrate completely within months. 3I Atlas is already leaving the solar system. It passed its closest approach to Earth on December 19th, 2025. It will fly by Jupiter in March 2026, and then it's gone, returning to the darkness between stars. But there will be more interstellar visitors. We've detected 3 in 8 years. As our telescopes improve, we'll find more. Maybe 1 per year, maybe more. The Vera Rubin Observatory, which will begin operations soon, is expected to detect dozens of interstellar objects per year. It will scan the entire visible sky every few nights, finding anything that moves. And ESA's Comet Interceptor will be waiting, parked at the L2 Lagrange point, ready to launch on short notice when a pristine comet or interstellar visitor is detected. The next decade of comet science is going to be extraordinary. We'll have continuous monitoring from space, rapid response missions, coordinated observation campaigns, and a growing database of both local and interstellar comets to compare. We'll learn about the diversity of planetary systems across the galaxy. We'll learn about the chemistry of star formation in different eras of cosmic history. We'll learn about the processes that shape comets and how they interact with their environment. And maybe, just maybe, we'll answer some fundamental questions. Are we alone in the universe? Could life exist on comets? Could interstellar visitors carry organic molecules or even microbes between star systems? So here we are. NASA's Punch mission has given us something unprecedented, a 40-day high-cadence movie of a comet drifting through the inner solar system. And in that footage, we caught a brief glimpse of an interstellar invader. This time-lapse is more than just a beautiful visualization. It's a scientific data set. It's a record of how comets behave, how the solar wind flows, and how these invisible forces shape the space around us. Comet SWAN, discovered by an amateur astronomer, tracked by NASA's newest spacecraft, observed by telescopes around the world. A native of our solar system making its first and possibly only visit to the inner planets before fragmenting and fading away. And 3I Atlas, the ancient wanderer from another star, zipping through the frame for just a few seconds. A reminder that our solar system is not isolated. We're part of a galaxy full of wandering objects, and occasionally they pass through. The technical achievement of tracking a comet every 4 minutes for 40 days cannot be overstated. This is the longest high-cadence observation of a comet ever conducted, and it's setting a new standard for how we study these objects. The collaborative nature of this discovery, amateur astronomer, space mission, ground-based observers, shows how modern astronomy works. Everyone contributes, everyone benefits, and this is just the beginning. More interstellar visitors are coming, more comets will be discovered, more missions will be launched, and our understanding of these cosmic wanderers will continue to grow. 2 comets, 1 local, 1 interstellar, both captured in the same footage by a spacecraft designed to study the Sun. It's a cosmic coincidence that gave us a unique opportunity to compare them side by side. So keep watching the skies, because the universe is full of surprises, and sometimes those surprises show up in the same frame. If you want to learn more about 3I Atlas and the mysteries surrounding this interstellar visitor, check out this video where I break down the latest Hubble images and what they reveal about this ancient comet. And make sure you're subscribed, because I'll be covering every new discovery as these objects continue their journeys through our solar system. Thanks for watching, and I'll see you in the next one.